first thing we have is a cart moving up an incline. Okay, and here's my cart, and it's moving up the incline, so my velocity is this way. Now, since my motion detector is going to be up here, looking down, and anytime the motion detector sees something moving away, it considers it positive, I am going to go ahead and assign down the ramp as the positive direction. So positive x is this way, positive y is this way. Okay, not that it's going to make a lot of difference in my picture. Okay, gravity always pulls straight down, or whichever way I just drew that. Okay, friction always opposes velocity, so I have that. The normal force is normal because it's normal to the surface, which means perpendicular. Okay, so the normal force is always perpendicular to the surface. So there's the three forces that affect that cart. Similar over here, still have my incline, but this time the velocity is down the incline. Okay, so the cart got to the top, slowed down, stopped, switches direction, now it's moving back down. Gravity, okay, gravity still pulls down. Okay, Fg. But now friction is actually going to pull up the incline, and the normal force is still perpendicular to the incline. Okay, so those are the forces we have to deal with. Now, really with gravity, you've got to pay attention because if along the incline is positive x, then gravity's not pulling in the x direction, and it's not pulling in the y direction. So we have to find its components. So this is Fg in the y direction, and this is Fg in the x direction. Okay, similar process over here. Fg in the y direction, Fg in the x direction. Now remember, this force right here doesn't actually act on nothing down here. This force is actually up here. Similarly, this Fgx is actually right there. The difference between these two diagrams, the motion of the cart, and because the motion of the cart is different, so is the direction of friction. Okay? Remember, friction always opposes motion. Okay? And so if the motion changes, the friction changes. Okay? During which motion would I expect the cart to have a greater acceleration? Well, remember, forces cause acceleration. Net force equals mass times acceleration. Since we're not changing the mass of the cart, all we're changing is the force. Okay, right? Friction acts down the incline, friction acts up the incline. I expect the acceleration to be greater when the force is greater. Okay, well over here, Fgx and F of friction, the force of friction, are in the same direction. They're both down the incline. Over here, one's up the incline, frictional force, one's down the incline. Okay, so I would expect up because friction and gravity are together. Okay. Alright, moving on. Would this be greater for large angles or for small angles? Well, this is a tricky question, but the frictional force is dependent on the normal force and the coefficient of friction. This isn't changing. We're using the same surface, same carts, okay, so it just says, how is this affected by the angle? Well, to answer that question, we have to know about the normal force. Gravity does not get affected by angles. Gravity always pulls straight down. Okay, but the normal force is perpendicular to the surface. Okay, and the normal force just opposes the component of gravity that's perpendicular to the surface. Okay, on an incline, this is a little bit less than if it was horizontal. Okay, so the difference will be greater for small angles because the friction will be greater for small angles. Alright, we set this up. We had an angle of 3.44 degrees. Okay, sketch your position and velocity graphs below. Okay, your position time graph should look something like this. Okay, here you're holding it. Here it moves up. Here it moves down, right? And then here it stops again. Okay, and your velocity graph, okay, let's see, you held it, then you gave it a very big push, and then it started to accelerate, then it came back down the incline, then it stopped again. Okay, so you had a graph that looks sort of like this. Okay, and again, this would be where it's moving up the incline, this would be where it's moving down the incline. Here it's moving towards the detector, here it's moving away from the detector. Okay, so negative velocity, positive velocity. The slope of the VT graph while moving up, this was 0.63. Okay, I just went to my graphical analysis and checked. And let's see, moving down, I had 0.55. Okay, now these were the slopes of the line. Slope of a velocity time graph is acceleration. Okay, it's change in velocity over change in time, acceleration, TION. Okay, and again, this is also acceleration. Why are the slopes different? Different forces, right? If we've got different accelerations, we've got different forces. And mostly it's because, in fact, it's entirely because friction changed direction. Now, I don't actually have all this data handy, so I'm just going to use these two. I just have the last data trial we did in class. So 0.63 and 0.55 are my accelerations. Okay? It says calculate the frictional force acting on the cart in both directions. So I'm going to split this up so I can have an up direction and I can have a down direction. Okay? And I got to have a picture. I cannot solve this without a picture. Okay, so here's my incline, here's my cart, here's gravity, Fg, here's gravity in y, here's gravity in x, Fgx, Fgy, here's the normal force, Fn, and this is moving up the incline, there's velocity, that means friction's down the incline, and I'm going to go ahead and assign down the incline as the positive x direction. Okay, positive x, positive y, good to go. Okay, and so I'm trying to find the frictional force. Well, frictional force is in the x direction. So let's see what I know about the net force in the x direction. Pulling down the incline, the net force in x is Fk. Also pulling down the incline, which remember I assigned positive, is the force of gravity in the x direction, Fgx. And according to Newton's second law, net force equals mass times acceleration. So all I have to do is find Fgx, and this is basically done, because I tell you the mass of the cart, and the acceleration we just measured is 0.63. Okay, so I can rewrite this as Fk plus mg, right? Force due to gravity is mg. Now this x I still have to deal with. That's this side of this right triangle. Okay, that means we're dealing with. Let me redraw this triangle a little bit bigger over here. Okay, I've got this side which is Fg, and then I've got this side which is Fgy in the y direction, and then I've got this side which is Fgx. By default, by definition, this is a right angle, so we can use some trig to solve for these two things, but we need to know one more angle in this triangle, because we know this side, that's Fg, that's Mg. Okay, sorry, I gotta plug in my laptop, it's yelling at me. There we go. Okay, so I know this is Fg, I know this is Fgx, I know this is Fgy. Okay, but I also know this angle, because the angle of the ramp is 3.44 degrees, the angle over here is also 3.44 degrees. Okay, which means this side is the side opposite the angle. And if I'm using the opposite side, then I want sine. Okay, and so that I can say that this is mg sine 3.44. Right, mg is the hypotenuse. Okay, 3.44 is the angle, and that'll equal the opposite side, equals m, which is 0.52, times the acceleration, which is 0.63. So now I just have to use my calculator to solve for these things. Alright, so here's my calculator. And all I want to do is show you guys a little bit about using a graphing calculator. I know you guys have your iPads, but I'm still old school. Okay, and if you're in degrees, it's fairly important that your calculator is also in degrees. So this is the mode button. Okay, and to make sure it's in degrees, you need to make sure degree is highlighted. If it's in radians, just arrow down to there, arrow over to degree, push enter, it puts it in degrees. Okay, second quit out of that, home screen, we're good to go. Okay, now all I got to do is take m, which is the 0.52, right, because the mass of the cart's 520 grams, which is 0.52 kilograms, times g, which is 9.8, times the sine of 3.44. And this is why I like calculators with a display. All right, push enter, and I get 0.305777. I'm going to call it 0.306. Okay, so back over here I have Fk Fk plus 0.306 equals 0.52 times 0.63 equals 0.3276. Okay, equals 0.3276. Subtract this over, and I get Fk equals let's see, 6 minus 0 is 6, 7 minus 6 is 1, 2 minus 0 is 2, and 3 minus 3 is 0. 0.0216 newtons. This is a very, very small force, but then it's a very frictionless cart, so I expect it to be small. Okay, so this is the frictional force as the cart moved up the incline. Now, before I come over here and do the downhill side, what should I expect the friction to be? Well, the normal force didn't change because the angle didn't change. The coefficient of friction didn't change because it's still the same cart. So I expect it to be exactly the same except opposite. Now, in experimental data, there's always a little bit of error, so we'll see how we do. Okay. Again, I'm going to start with a picture. Cart, but this time, okay, the one force is going to be different. I still have gravity. I still have gravity in x and y even. So gravity Fgy, here's Fgx. But now the normal force, Fn, is this way. And since the cart is moving down the incline, friction is moving up the incline. Okay, I'm going to simplify this. I'm just going to draw the two forces I care about. Okay, because in the net force and y they cancel. Okay, I've got Fgx, which is down the incline, and I've got the frictional force, which is up the incline. So now I can do the same thing. Net force in x equals down the incline is positive, so Fgx minus Fk, which equals ma. Okay, and so I actually still know ma. Well, no, I don't. The acceleration changed, right? Because it changed for down the incline. But I do still know Fgx. This is still mg sine theta. The angle didn't change. So this is still 0.306 minus Fk equals m, which is still 0.52, times the acceleration, and I got to check on that one, 0.55, okay, times 0.55. So now, if I subtract over that 0.306, I get negative Fk equals 0.52 times 0.55 minus 0.306, negative 0.02 newtons. So the frictional force, Fk, equals 0.02 newtons. And I subtracted it here, so this is giving me the absolute value. So this is right. The frictional force 0.02, over here I have 0.0216. That's pretty much exactly the same. Okay, we're close enough there that we're not going to argue with it. Okay. Now, from here it says, what's the coefficient of friction between the cart and the ramp? Well, I know that the frictional force is equal to the normal force times the coefficient of friction. Well, I just found the frictional force is 0.021. Okay, I'm kind of averaging those together. 0.021, and so this is equal to the normal force times the coefficient of kinetic friction. Now, on a horizontal surface, the normal force is Fg. On a slanted surface, it's Fgy. So this equals mg cosine 3.3 or 3.44 degrees, and right, that's the y component of this triangle up here, and so times the coefficient of friction, and so I get mu k equals the frictional force divided by, that's supposed to be a sub k, that's kind of horrible. I get the frictional force divided by mg cosine theta. And so if I put in my numbers real quick, that's 0.021 divided by m, which is 0.52, times g, which is 9.8, times the cosine of 3.44. Okay, and so 3.44 cosine times 9.8 times 0.52 is 5.08, 5.09 essentially. So 0.021 over 5.09, this is going to be really little number, 0.021 divided by divided by 5 0.09, okay, and that's 0.004. So I get a coefficient of friction of 0.004, which is little, but we expect it to be little. It's a fairly frictionless cart. Okay, suppose you had a 500-gram mass of the cart. How will this affect the cart's accelerations? Well, now let's think about this. Okay, why does the cart move down the incline? It moves down the incline, or accelerates down the incline, because of the x component of weight, the x component of gravity. Okay, so this is Fg, this is Fgx. If I increase the mass, this force gets bigger. But what opposes it? Friction opposes it. Okay, and so the normal force would also get bigger if I increase the mass, which means the frictional force would get bigger. Okay, so it should be that mass does not affect acceleration. Okay, it should be that. We'll have to see what it actually works out to be. Okay, so try it again.